All right, kiddos, I'm back with the next part of lesson 3A. So we're looking at these several examples. If we have Newton's universal law of gravitation, where the gravitational force is equal to gravity's constant times the product of the two masses that are interacting over their separation distance center to center, then we can take a look at how changing different things changes that force. I've got the answers to the prompts I asked you to solve for on the screen. Please check and see how you did. Okay. In this equation, instead of r, right, in this problem, they're using a lowercase d as separation distance, and that's a common change in notation from one resource to another. Okay, so it's easy to see in this equation that as if you double one of the masses, you would double one of the amount of force in between them, right? Force and mass are proportional. The tricky thing is that the distance that they're separated is an inverse squared relationship. So if we take a look at this answer here, what happens if you double the distance that they're separating? A lot of people would say that the force would be halved, right? But the total distance is squared. Okay, so if you double that distance, double the distance is squared. So what happens is you get G M M, whoops, that's a 2 over d squared, but also that 2 is, that 2 is squared, and that turns into a 4. So what we have is if you double the distance, that gets squared, and on the right-hand side, you've got an extra factor of 4 in the denominator, which means there must be an extra factor of 4 in the denominator on the left-hand side as well. So that means you double the distance and the force is divided by 4. Similarly, if you halved the distance, that would mean that you, right, half is squared, so that turns into 1/4. Okay, and what's 1/4 in a denominator, right? Invert and multiply, that's 4 times the force. Okay, 1 over 1/4 is 4. Okay, so let me know if you have any questions about that, but that's a proportionality way to solve these problems, whether or not you know the values of the mass and the values of the distance. You can still say proportionately how many times bigger or smaller can the force be when certain values are changed. Okay, I'm going to skip over those. All right, you guys. So the next concept that we want to talk about when we're talking about gravity and forces that are acting between masses is an idea called gravitational field strength. And this is also known as the acceleration due to gravity, right? Little g is the abbreviation for the gravitational field strength. And on an IB style question, almost always will they ask for gravitational field strength. Almost never will they describe this concept in terms of acceleration due to gravity, just to make sure that you know what they're asking for. It's a conceptual question. Okay, this gravitational field strength is 9.81 meters per second squared on Earth's surface. But that totally changes if you're up in orbit, or if you're a distance away from the Earth that's near to kind of where the moon is. Okay, so if we know that the force due to gravity is G M M over R squared, again, you've got a big mass, a little mass, like the Earth and a satellite and their center's separation distance. Remember, another name for FG is a object's weight. And there's supposed to be an I in there, weight. And if we're asking what is the weight of the satellite, right, they're talking about the weight of the smaller mass. This equation that we've been using for weight is still valid. Okay, this little m is the same little m as this one over here. Okay, so we can calculate an object's weight at any place in the universe using our universal law of gravitation. And then if we know the mass of an object and the gravitational field strength, we can find the weight that way as well. So we can actually say, by solving this equation, gravitational field strength equals Fg over m. Okay. Gravitational field strength equals weight over m. Right? And if weight is this, we can say GMM over R squared divided by m, right, weight over mass. And it turns out these little masses cancel out. G capital M over R squared. So let's rewrite that again. Gravitational field strength, or the acceleration due to gravity, equals G times the big mass, like the planet an object is near, over R squared. This is the equation for gravitational field strength, or acceleration due to gravity. So what we just showed is similar to what we found when we were working on the vertical motion lab. Awful lot of you found in your conclusions for the vertical motion lab back in semester 1 that an object's acceleration doesn't depend on mass, right? Or an object's velocity at landing is not dependent on mass, right? And we just found that to be true, right? See, when we calculate the gravitational field strength, or the acceleration due to gravity, the mass of the object that's being impacted by the gravitational pull of something like a planet cancels out. Okay, so that's your conclusion is supported by Newton's universal law of gravitation. Okay, so let's use this equation to find the gravitational field strength of someone that's on the surface of the Earth. Okay, let's actually do a little bit of plug and chug here. So we know what we expect it to be. G equals big G times here. If we are on the surface of the Earth, capital M will be the mass of the Earth over R squared. Where will we be located near the surface of the Earth? What will be R? Well, that would be the radius of the Earth, right? The distance from the center of the Earth to the center of us. And in the grand scheme of things, we are like a couple meters tall, maybe. 1 meter is not going to make a difference in this problem. Okay, so if we were to solve this, big G is 6.67 times 10 to the minus 11. The mass of the Earth is 5.98 times 10 to the 24. That's in kilograms. And then the radius of the Earth is 6.38 million. So 6.38 times 10 to the 6 meters. Okay. Now remember, those distances are in meters. 6.38 million meters, again, the radius of the Earth. If we add the distance from the surface of the Earth to the center of us, right, we'd add another meter to get up from our feet to about our belly buttons, and that is not significant. in this. And also don't forget, right, that we want to square that distance. That's a common mistake. Right? When you're doing these problems, make sure that you're knowing how to put in values into your calculator in scientific notation correctly, that you're using parentheses, probably overusing parentheses, because different calculators apply order of operations differently, and I don't want you to be multiplying a negative 11 times 5.98. So like stick these things in parentheses. All right, and when you calculate that out, guess what you get? 9.8 meters per second squared. What's another unit that we could use for gravitational field strength? Remember up here, we said gravitational field strength is force over mass, so its units are either meters per second squared or newtons per meter. Both of them are absolutely valid. So meters per second squared or newtons per meter. And so this not only, the gravitational field strength doesn't only tell how fast something is speeding up, how much it is speeding up every second, but it tells us how much force is being exerted, or sorry, newtons, nuts. Erase. Force per mass is in kilograms. Good thing I caught that, you guys. That would have been bad. Newtons per kilogram, right? So that's telling us at a specific location in space, away from the center of your planet or from the center of the Earth, how many newtons of force are being exerted for every kilogram of mass an object has. So this is telling us on the surface of the Earth, a person or other object is experiencing 9.8 newtons of force for every kilogram of mass that they have. Okay, and that's another way of thinking of gravitational field strength. All right, the way that we represent the strength of gravity's field is with something that's called field lines, gravitational field lines. We will have these lines drawn also when we talk about electric fields. Okay, so gravitational field lines, or any field lines, are drawn using arrows. Okay, so let's say this is the Earth. Right, the gravitational field lines are drawn radially and equally spaced towards the Earth, and the arrows are pointing towards the Earth because that is the direction that an object anywhere around the Earth would be pulled, right? It indicates the direction of the force. Okay, so if you've got a circular object like the Earth, the gravitational field lines will be spaced evenly pointing towards the Earth because any mass near the Earth would be pulled in. Okay, the density of the field lines indicates the strength of the gravitational field, right? And so if you're closer to the Earth, the gravitational field lines are closer together, indicating that an object at that location away from the Earth would experience a bigger force, right, due to gravity. Out here, fewer gravitational field lines, or so they're the same number of gravitational field lines, but they have a smaller density. They're not as close together, indicating out there an object would feel less force. For our purposes, on the surface of the Earth, the ground appears flat, and so from our perspective, the gravitational field lines are evenly spaced anywhere in our perspective. All right, so try this problem, and I'll see you in a minute.